Okay, here we go. Simple Machines video 2. Remember, take notes. They are for grade. You might need to watch this video more than one time. Fulcrum. So before we get started, I'm going to just give you the parts of the lever. There's the fulcrum, which is located at the point where the lever rotates. So here you go. That's the fulcrum. The input force and input distance. So that's where the force is being put into the lever and where you move with that force. So let's say here's the force input. I push this down, I move a certain distance, that's the force, that's the input distance, all right? So force input is the push that I push it with. The distance is the amount I move the lever, okay? Output force and output distance, so the action of the lever, and then the distance the output force moves. So here I have the output force, and so if I push down here, I'm going to lift up here, and the amount that I go up, that's the output distance. Okay? Now, conservation of energy, how can that be? So remember, work input must be equal to work output. So here, if I push this down, the distances that I travel will not be the same. I'll push further down. This won't go as far up, right? But what's going to happen is that I'm going to push down. I'm going to travel a larger distance with less force, right? Whereas here, I'm going to travel a shorter distance with more force. Okay, so remember the force input times the distance will always be equal to the force output times the distance. If you increase the force input, you will decrease the force output, okay? But it'll always be balanced. There's always going to be an equilibrium. Okay, so what does this have to do with the mousetrap lever? All right, so the mousetrap lever is a special kind of lever. In this case, the mousetrap lever is the fulcrum is at the exact same place that the force input is, right? So there's a spring here. The spring has potential energy, right? There's going to be a rod or a lever attached to the spring, okay? And so what that means is that there's going to be a very small input distance and a very, very large input force. Okay, very large input force. So what that means is that what you're going to have is a very small output force, but a very large output distance. So the longer you make this lever, the more distance the lever will travel. The shorter you make the lever, the less distance the lever will travel. However, the longer the advantage of having a long lever is that yes, you get great distance, which means you can pull the string for a long time. However, the longer the lever is, the less output force there is. Okay, so if you have a really large distance, you're going to have a small output force. So something to think about. Next, wheel and axle. So by turning a wheel, you are moving a large distance, okay, with a very small force. So if I move this wheel right here, I'm going to move it a really large distance, but it won't be that much force, okay, and it will move the axle. The axle will move a small distance, but with a very large force. So that's really useful when you're hauling things like this. Okay, the other way around is when you move the axle. This is the axle. This is the wheel. By turning the axle, you're moving a very small distance, but it requires a very large force. But what that means is it makes the wheel travel a very large distance. Okay, so I'm going to show you these videos really quickly that hopefully this will help out.
Machine with two different sized wheels on the same axle, or with two things that act like wheels. This is one wheel, of course. The second wheel is here, the circle.
So this is like the axle.
They go around. The circle acts like a wheel. You apply a force to the pedals. Through these arms, the pedals make the axle turn, and the axle makes the large wheel turn. When one wheel makes one complete revolution, so does the other wheel. This is the distance your foot moves in one revolution, the circumference of the small wheel. But this, the circumference of the large wheel, is the distance you roll forward in one revolution, much farther than your foot moves.
So when you have your mousetrap car, you're going to be moving the axle. Okay, so you'll be moving the axle a very small distance. And every time you move the axle around one time, you move the wheel around one time. So you're increasing the distance. The bigger the wheel you have, the more the distance you go. However, the more force you will need to move that wheel. Okay? So this is when you need to start thinking about these ideas of inertia. Sometimes it's better to make the car go really fast and then the inertia will keep it going. Those are the decisions that you'll have to make. Here's another part of the video.
Does this mean you needed to apply a lot of force here? Yes, it does. With wheel and axle machines, you always trade force for distance. For distance for force. And because you always trade one for the other, you can't multiply both force and distance at the same time.
Okay, so the more force you have, the faster your car will go. All right. But the more distance you have, maybe, well, I mean, that's kind of what we'll have to figure out. Um, okay, so in your mousetrap car, what's going to happen is that when your lever will pull a string, that string will pull your axle. That axle will move the wheels, okay? And so with both the lever and with the axle and wheels, you're increasing distance, okay? And so there are two different ways of making a car. You can make a car that you think is going to travel a really long distance, or you can make a car that travels really quickly. So it's got a short lever and small wheels, but it travels really quickly. And so sometimes those are better, but something to think about, okay? There you go.